Welcome everyone to another video, and doing something a bit different today. I've decided to throw my hat in the ring when it comes to NVIDIA's 12 volt high power connector. I haven't done a lot of content with computer related stuff on my channel, but I have a long history of overclocking and tinkering with computers, going back a very long way, and I feel like I can contribute some stuff to this space. There's been some good information that's been put out there by DeBauer, by Buildzoid, by Gamers Nexus. There's also been a lot of junk content out there from other YouTubers that are just regurgitating stuff they read online and not really adding anything meaningful. So I have built this entire setup purely to torture 12 volt high power connectors, to test them in a way that is repeatable, in a way that we can analyze and get useful data, hopefully. So anyway, let's get started. Right, so the 12 volt high power connector, I've seen a lot of information online about this, and I feel like the biggest thing we need to tackle first is everyone's saying that this connector has absolutely no safety margin in the application it is being used in. I've looked over all the data sheets, and to a point I agree. Yeah, it's rated for 9.5 amps per pin. There are 6 12 volt pins, 6 ground pins, 12 pin connector, and it's running at 12 volts. So 6 pins, 9.5 amps per pin, 12 volts equals roughly 680 watts rated for this connector. Fine, that's pretty much near the limit already on the data sheet. Now, no manufacturer like Molex, for example, is going to build a connector rated at 9.5 amps per pin and ship it that way, right on the limit of failure. They will build a safety margin into the design of the connector. If it is right on the bleeding edge of melting at its rating, they would not sell the connector. These connectors are used in industrial applications, server applications, many other things. It would be just absolutely nuts for a designer to put a connector on the market like this and it's right on the point of failure. So we're going to address that in this video. I want to figure out 3 things. How much current per pin can we put through this connector before it is on the verge of failing? So it is rated at 9.5 amps. We're going to see how far we can go beyond that as a single pin. And then we're going to look at how much power can this connector handle overall without failing. And then I think as a third sort of thing, we're just going to go all in. We're going to dump as much power into the connector as we can and try and get it to melt. Because let's be honest, everyone wants good YouTube video content. So let's destroy one of these connectors. And I built this entire setup to do that. So I'm going to just show you everything we've got here and why I built it the way I built it. Right, so diving into the setup, I don't have a massive YouTuber budget, and that is one of the most frustrating things about this whole situation for me. So if you guys can, help share this video, help me grow a little bit, I can probably take this even further, but this is about the limit for me at the moment because this cost a lot. I could probably buy a brand new graphics card for how much I've spent here. So 3 power supplies here. These are server power supplies by Delta. Very robust, quite cheap, and I chose these because I'm not worried about blowing them up. They do have individual spade connectors, which also made them ideal for hooking up to very large gauge wires, which feed into these bus bars. I've modified these power supplies so they are not insanely loud, but they are also working together in sort of a sharing, teamed up configuration. And they are 750 watts a piece, so we have 3 of them, so 2200 watts roughly at 12 volts at our disposal here, which is more than enough for anything we need to do here, but to try and keep the voltage very stable under these really heavy loads also. So they feed into these large brass bus bars. Everything here should be way over spec. They shouldn't get crazy hot. Everything should be good there. And this is sort of the input side, and then we have the output side with another set of brass bus bars that will flow a lot of current into these DC electronic loads. I have 4 of these. They are rated at 400 watts per piece. So we have 1600 watts of total capacity to flow through this connector to try and get it to fail. We have very large wiring here, also way over spec for what we need. I can technically add more loads if I need to, but I am hoping 1600 watts will be more than enough for this entire setup. So we have a thermal camera on standby. This is quite a high-end model, very high resolution, even by modern standards. I think it's only one below the highest resolution thermal camera you can get. The only limitation it does have is it can't do video recording while showing temperature overlay, which is a bit of a disappointment. We have a current clamp here. I mean, every YouTuber seems to be using this in regards to this connector. I want to stress these current clamps are not that accurate, and you should not really trust them as gospel. They give you a ballpark figure, but they are not perfect. I have this one connected to my multimeter. It's pretty high end, has a lot of great graphing functions and whatnot. It's just a rough sort of thing, so I can confirm that we have equal current across the wires without having to disconnect everything. These digital loads do show current very accurately, way more accurately than that thing does. I have confirmed it with other tools that I have at my disposal just to confirm and sanity check that we can trust what these are saying, and we can, so that is all good there. So for the female side connector itself, I decided to go with these Be Quiet brand cables. I was able to get these pretty cheap, and I don't mind sacrificing them. They're not crazy expensive. Cut the ends off, and it turns out that these wires, if you cut everything back, they have two 18 gauge wires that are crimped together, and then they go into single 16 gauge wires, which is what we're left with here, into this connector. Been pretty impressed with the quality of this cable overall, so I'm happy for this to be my reference point, at least for the moment. And when it comes to the connector itself, I've made two different variations. We have a PCB mounted connector. This was my sort of second iteration of this. So it's a single-sided PCB, so I am limited with what I can do. I had to make this at home. The connector cutout is problematic on a single-sided PCB because I have to route the trace around the sides of it. So I added some extra wire through the middle here and built it up to try and handle the current that's going through. So we've got 12 volts coming down each side, and I'm hoping it's sort of spreading evenly there, and a large ground plane in the middle. And I think with all these wires here and all this, you can get some idea and maybe a little bit of respect for what this connector is actually dealing with the amount of current that is flowing through this whole thing at 12 volts. I mean, this is a lot of copper we're dealing with here. So the alternative I also had, this was my first attempt, is I have a connector soldered directly onto wires. And what I found in my early testing with this is that the heat from this connector and the current draw is wicking down into the copper in the wire and sort of spreading out evenly. And I wasn't super confident that we were getting a realistic example of what this connector can do, because all the heat was just getting pulled down into the wire very rapidly. So yeah, that is another alternative that we're looking at, along with the PCB type mounted connector. So let's get started with the first point and see how much current we can put through a single lead or pin on this connector. So excuse the noise, this is going to be quite a loud video from this point forward. I've already got it set up. We have just one wire running to the connector at the moment, and as you can see here, we are loaded up. So we're looking at about 35 degrees as the hottest point anywhere on the connector, and that is slightly over the rating at 10 amps, supposed to be 9.5, 120 watts. I'm going to just start cranking this up because I already sort of know what's going to happen, but I'll take you through all the levels. So what we are going to do is we are going to double this to 20 amps, and that's 237 watts now. We're starting to get a bit of voltage drop. So that's the input side, that's the output side for future reference. And we're going to see this start to heat up pretty quickly. But how far will it go? So it's been about 10 minutes and the temperature has leveled out at 62 degrees. Nothing really to speak of yet. Yes, it is hot, but it's not anywhere near failure. So Still no signs of failure, 91 degrees, so it's getting right up there now. I've ended up turning on the second power supply. We're going to go a little bit further. So I'm going to take this up to 35 amps total. That's as far as I'm going to go with this. It just exceeds one of these, so we need to use two of them now. And I'm pretty sure it's going to pass the 100-degree mark. Oh, it's already passed. Look at that. So just so there's evidence, that's 35 amps that have been through one pin and no visible damage. Same deal as before, except I've swapped over to the PCB setup. Single wire again, 33 degrees, same as before. I've gone for sort of a side angle this time so we can see the PCB a little bit better. And we're going to go up to 20 amps again. No issues so far, about 54, 55 degrees, pretty similar. 20 amps, so that's double its rated capacity. Up we go. Temperatures pretty similar. Not much difference with the PCB, so we will do it again. We'll just go up another 5, so 35 amps or 3.5 times the rating of this connector. So we're done with the single pin testing. 35 amps, 3.5 times its rating, which was really impressive. Yes, it did get really hot, but it still didn't melt the connector, which was really impressive. So now we're going to do the whole connector, which is going to generate a lot of heating around those pins. I'm sure we're not going to be able to go as far, but let's just see what we can do with the whole connector. So I've got all this set up. I've got you hard mounted, just looking at the thermal camera. I'm going to have to just leave you here because we're going to have to start going through this a little bit quicker. We're going to go up in 100 watt increments. We're at 600 watts at the moment. It's just idling there. So we'll go 600 watts, 700 watts, 800 watts, 900 watts. We'll just keep going until the temperature gets too hot, and we'll stop there. There'll be a 5-minute dwelling time at each setting change. So 600 watts at 5 minutes, and then we'll go to 700 watts at 5 minutes, and we'll increase it after that 5-minute interval to give temperatures a chance to just sort of equalize and get sort of an accurate measurement. So I'm going to start bringing this up. We're going to go straight up to 700 watts, increasing to 800 watts, increasing to 900 watts, increasing to 1000 watts, watts and holding. Temperatures are still pretty good, I guess. Increasing to 1100 watts. 1100 watts and holding. This room is getting very hot. So I think this will be the last increase. We're going up to 1200 watts. 1200 watts and holding. This is pretty nuts. Oh, I'm gonna have to take my shirt off in a minute. It's getting very, very, very hot. All right, I'm stopping it there. I'm gonna let this cool down and we will set up for the new configuration. Right, so everything is set up. Same deal as before, starting at 600 watts, going up 100 watts at a time, 5-minute dwell time at each power increase, and let's just see where we end up. Increasing to 700 watts. Looking good so far, 700 watts, as you would expect, so we're going up to 800. Looking good at 800 watts, increasing to 900. Still hanging in there, increasing it to 1000 watts. Right, so I'm calling this one here, I think. It's been over 5 minutes at 1000 watts, and it's getting very hot on the PCB, but I really think this is a limitation of my PCB. So I've decided we're not going to stop at 1000 watts, we're just going to keep going up. So I've already gone up to 1100, and it is hanging in there, but we are getting very hot. And we're just going to keep going up. Still no signs of anything. I'm going to increase it to 1300 watts. All right, I think I'm starting to see some smoke. I'm sure I saw something. There it is. So it's starting to fail at about 170 degrees. I'm not even sure if that's the connector or the PCB. Hang on, I'm going to move this out of the way. There you go. Temperature is 177 degrees Celsius. Just to reiterate, this is 1300 watts running through this. Alright, I'm going to pull the connector off and see if it's still intact. And if it is, we're just going to keep going. Well, it hasn't melted. I actually think it was just flux on the PCB from that getting so hot. There's no damage that I can see. Still looks intact. So I'm going to increase it to 1400 watts, I guess. Holy crap! What just happened? Ah, that's hot. Hot, 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 hot. No way. No way. It desoldered the connector. Ha! Hot. Alright, hang on, I've got to turn this off. Well, this project is just full of surprises. Yeah, it actually managed to desolder itself from the board. But not only that, it managed to reflow this entire area, and all the solder has run down to here. So all those pins are clean now. There's no solder really left in that area. This area up top seems to have held up better, which is funny because I thought this was going to be the weak point because the trace is thinner. But I did build it up a bit also. I went back and looked at the footage. It got up to about 220 degrees, which is really, really hot. And it didn't really come across on camera, but it was really loud when the connection broke. There was like 120 amps running through this connection when it popped open. Yeah, it's warped the PCB massively also, which I guess is what helped launch the connector off. So yeah, the heat warping is just nuts. Absolutely nuts. So that's dead. Really surprising and very cool. But the question is, did the connector survive? Ow! Poking myself. No way. It's intact. It didn't melt. Okay, that's amazing. It looks like we're going to have to go again. And I got my connector back. I guess I'm going to go back to the wired version and see what happens. So I've got the connector loaded up again, and it's pulling, what are we, 1200 watts at the moment. Definitely starting to see some inconsistent behavior. Current draw is different across each pin, but it seems to improve the more it warms up. But one wire was only pulling like 6 amps when it was cold. So yeah, there's definitely damage to the connector now. Now at 1300 watts again. Temperatures are a lot more under control this time. Now up to 1400 watts. I don't know if I'm going to have the capacity to do this, but we're going to keep going. 1500 watts. I don't think it's going to fail at 1500. I just don't think it's hot enough yet. All right, I'm going to take it to the limit. 1600 watts. Oh, I don't want to buy another load bank. I really don't. This is wild. The current has evened out across all the pins. Now they've heated up. Very weird situation. All right, I'm calling it there. We're not going to get it. Start cooling it down and we'll see if we've got any damage to the connector. Right, so I'm calling this video here. It's been one hell of a journey, and I didn't burn out the connector, but I certainly burnt out myself in the process, and I need a bit of a break and have a ponder about where we go from here. I did not get the outright melting that I was so ambitiously thinking that this would be easy to do with 1600 watts of load, but I like to be surprised as well. And we did not melt this connector, even at 15 minutes at 1600 watts. Yes, we did destroy the PCB one, but I'm not going to blame the connector for that. I think it was my PCB, and these traces need to be bigger. And everyone's going to say to me, why didn't you make it bigger? Because I didn't know how far to take this. I could go overboard with this and fill it with copper wire and everything and make it a massive thermal mass and conductor to get all the heat and current out. But that's probably not representative of what a graphics card is either. So I decided to start here and see what happens. But I believe with what Molex said in its data sheet that the thermal mass of the PCB plays a big part in this connector's capabilities. And that probably needs investigating more. And I don't have any sort of a reference for how much copper is normally in a graphics card that's attached to one of these connectors. And we're talking about a lot of current here. People need to give this connector a bit of a break, I think. We're talking massive, massive amounts of current. And me personally, my opinion on this whole situation is that PCs need to make the move to 24 volts. Me personally, I want to see them go to 48 volts and be done with this garbage forever. And for anyone who's not aware, volts times amps equals watts. As this stands, I would have to go and buy another 2 DC electronic loads probably. I've already purchased 4, which cost me a lot of money. That was just nuts, and I don't really want to go any further down this rabbit hole unless this video does really well. So I don't normally say stuff like this, but if you can help share and grow this a little bit, maybe I can justify just going in at this even more. I will say that, yes, I know these connectors are melting in graphics cards, but there's something else going on here. It is not just the connector has no safety margin. There is more to this than meets the eye. And I know Gamers Nexus has tested the connector being half unplugged and everything, but I think honestly, even with 2 pins being connected, you're probably, or maybe, 3 or 2, you're probably still not going to be in a scenario where this thing's going to melt. So I don't know if this is down to China garbage cables with bad crimping on the wires, bad retention on the pins, or something else. We need to go further with this, I think. I will just say that's one interesting thing, and I don't know if it's intentional or not. This connector seems to have self-healing capabilities. Ooh. So when it heats up, I mean, we did start to see inconsistent heating across the wires, which means the current draw was not even. But after the connector heated up to a certain point, it corrected itself, and then everything settled down and we had even current draw across every pin. I cooled it down again, heated it up again. That inconsistency was gone the next time. So it seemed to reform itself and then it was set again. It's wild. I don't know exactly what's going on there. Further investigation required, I guess. So I hope you enjoyed this video. Yeah, I'm a little disappointed, but you know, we got some action with the connector popping off and desoldering itself, which was really impressive. But we need to do better. Let's see how this goes. Maybe we'll come back for round 2. Until then, I will see you in the next video.